In this video, we are going to discuss integrations as shown in example 22. Example 22, example 23, and example 24 forms a group of integration type. In these three examples, the integrand involve an expressions in the form of the square root of a squared plus x squared, or the square root of a squared minus x squared, or the square root of x squared minus a squared, where a is a constant. In example 22, the integrations of the type where the integrand is 1 over square root of 4 plus x squared. This integration involves a denominator of the form square root of 4 plus x squared. We are considering a denominator where it is expressed as a form of a squared plus x squared enclosed in a square root. Here, the a squared plays a role of 4, so we can consider a is 2 in this particular example. The expression of this square root term can be interpreted by referring to the Pythagoras theorem applied on a right triangle. The term a squared plus x squared in the square root looks like the hypotenuse of an right triangle with a side of length a and a side of length x. So it is quite straightforward to realize that if you have a right triangle with a base a and a side x, then the hypotenuse is just the square root of a squared plus x squared. Here, you consider the x as a variable. The variable of x can also be parameterized in terms of the angle theta, where the theta represents the angle that characterizes this right triangle with a height of x and a side of length a. That is how you interpret this expression in terms of the Pythagoras theorems written down for an right angles with this side and parameter theta. The next step to do is to express the parameter x in terms of theta. It is then quite straightforward to recognize the relationship between theta, a, and x by saying that the tangent theta is just the opposite divided by the adjacent. So you bring the constant a to the left, you have then a relationship that relates the variable x to the variable theta. Once this trigonometric substitution has been determined, we can then proceed to express the integrations in terms of theta. So to proceed with the integration, we have to work out what is dx and 4 plus x squared in terms of theta. To this end, you need to differentiate this substitution. Differentiate with respect to theta will lend you to a secant square theta equals to dx d theta. Multiplying both sides with d theta, you get the right hand side to be the differential of dx. Therefore, dx is a secant square theta d theta. As such, we write down dx as a secant square theta d theta. For the denominator, we need expressions for a squared plus x squared. I will write down a squared plus x squared by referring to this relationship. A squared plus x squared is simply equals to a squared plus a squared tangent square theta. 1 plus tangent square theta is just the secant square theta due to the identity that 1 plus tangent square theta is just secant square theta. The square root of a squared plus x squared can then be written down to be a squared secant square theta. Remind here that a squared is 4, so that a itself is 2. Up to this point, we have shown that the integrations with respect to x for 1 over square root of 4 plus x squared has been converted into the integration with respect to the variable theta. The integrations here can be simplified further. The denominator is a secant theta. So the a term gets cancelled off, so is the secant term. So that led to secant theta d theta. Remember, the integrations of secant theta has been discussed in module 1, example 7, which is simply the log of secant x plus tangent x. So we end up the answer to be secant theta plus tangent theta plus n constant. However, the integration has not been done yet because we have to convert secant theta and tangent theta back to the expression of x. So the following steps is to see how the secant theta and tangent theta can be expressed in terms of x. This could be done by referring to the definitions that relates x to tangent theta. This is just the original triangle that was written down a minute ago that represents the parameterizations of a tangent theta equals to x, or rather tangent theta equals to x over a. Secant theta can be easily expressed in terms of theta by referring to this triangle. Namely, secant theta by definition is 1 over cos theta, which is by definitions equals to a divided by a squared plus x squared. Tangent theta is simply x over a, which is just the same as this one. We then write down the log of secant theta plus tangent theta in terms of x. So the results of log of secant theta plus tangent theta look something like this, which could be further simplified. Split the log term into two parts. The log of the absolute values of a squared plus x squared in the square root plus x minus ln a plus n constant c. So I write down the original integration on the left hand side. A here should be replaced by 2. So I use this symbol, a equals to 2. And that is the final expression for the integrations of 1 over square root of 4 plus x squared. As a conclusion, to integrate the function with a denominator square root 4 plus x squared, we use this trigonometric substitution, which represents a triangle that is written down by identifying this square root term to be the hypotenuse. It is important to draw this triangle correctly so that you can arrive at this trigonometric substitution rule. Once the triangle is written down, then you'll be able to decide the substitution rule for x in terms of tangent theta. Then you would translate the integration in terms of x into the integration in terms of theta. Some algebraic rules would then lead you to an integrations of the form secant theta. The integration of secant theta was obtained from the previous integration, which is log of secant theta plus tangent theta. You then have to revert the secant theta and tangent theta back to the expression of x, again by referring to the triangle that represents the parametric substitution, where the secant theta is simply equals to this term and the tangent theta is just simply equals to this term. Finally, when you put everything together, you get the integrations of this by identifying the a as 2